Hi, I'm going to be talking about this paper, Optimal Learning of Quantum Hamiltonians from High Temperature Gibbs States, which is joint work with Jeongwan Haah and Kothari. Because this is a recorded talk, there will probably be stuff on the slides that I don't explain very well, and the pace might be somewhat fast. I'll try to be cognizant of that fact, and hopefully the words that I'm saying will still be comprehensible, even if the slides are a little bit difficult to read. Okay, let's begin. So this paper is about parameter learning of quantum Hamiltonians. The setting here is that we have some Hamiltonian H, which is over n qubits, and we imagine it having constant locality in a spatial dimension that's also constant. So I've drawn a diagram here where I represent the qubits as these circles. And I have terms E1 through E4, and these terms are local because they act on, for example, E1 acts only on qubit 1 and qubit 2 and is the identity on all the other qubits, and so on. So that makes E1 2 local. And it's in ambient dimension 1 because it's just on this straight line lattice, and then the terms are local within that lattice. They only touch neighboring terms. Okay, so that's the sense in which I mean that it's local. And so I'm imagining that H is a linear combination of these terms that I've just discussed. And attached to these terms are corresponding parameters, which are the things that we want to learn. So we will assume that these EAs are products of Pauli's. Basically, if you have some local term, you can imagine like writing it in terms of a linear combination of products of Pauli's. So this is sort of just picking a particular basis for that. And we are supposing that we can prepare copies of the Gibbs state corresponding to the Hamiltonian H at a particular inverse temperature beta that we know. So the idea here is that we have the ability to prepare these Gibbs states, which maybe we have a lab and we can make the state evolve with like a heat bath attached to it or something. And so we can get these Gibbs states. And the goal is to understand the quantum system that governs the sort of dynamics. And so we want to learn the parameters lambda A. And so this is the setup for the problem. And the two criteria we'll use to analyze the success of our algorithm is, first of all, the sample complexity, which is the number of copies that we need to estimate all the parameters to epsilon error. And secondly, the time complexity, which is the amount of computation time that we need to get these estimates once we have the samples. And something to note is that we would expect this problem to be hard as beta goes to 0, because when beta goes to 0, then rho becomes, it sort of tends to the maximally mixed state, or the identity. And so you lose all the information about H. And so you're not able to estimate the parameters. Similarly, as beta goes to infinity, you expect hardness, because then rho converges to the ground state. And again, you lose information. So these are the two regimes in which you would expect hardness. Now, let's look at the state of the literature on this problem. This is actually a fairly well-studied problem if you restrict to classical Hamiltonians, so in the classical setting. There is a folklore sample complexity upper bound, like an algorithm that gives optimal sample complexity and optimal time complexity. I say this time complexity is optimal because it's linear in the size of the samples, in the size of the samples, because each sample you're thinking of, right, it's n qubits per sample, or per copy of the Gibbs state. So in order to read everything in, you need the number of samples times the number of qubits. So this is indeed optimal. It's linear time. And there's a corresponding matching lower bound. The lower bound is not for the same problem. The lower bound is for the problem where the terms are also unknown, but fundamentally this is like the optimal algorithm. And In the quantum setting, much less is known, actually. So there's one paper, which I'll refer to as AAKS, which gives a sample complexity lower bound that's much weaker than what you would expect from the classical literature, and a sample complexity upper bound, which is like sort of it's sort of polynomial in all the right parameters, but seems to be lossy in, for example, the betas and the n squared term that's here. And the interesting thing is that this sample complexity algorithm does not come with a corresponding time efficient algorithm. The authors do assert that a time efficient algorithm is possible for small beta. So this is a high temperature regime. And in this case, when they assert that you can get a polynomial time algorithm, they don't give too many details on this. And so I'm just guessing this runtime to some extent, but certainly it should be larger than their sample complexity upper bound. Now, this is sort of the state of the literature for the quantum Hamiltonian learning problem. And so what we do is we essentially close the question of sample and time complexity in the high temperature case. So we take this sample complexity lower bound and we indeed like show it that the same thing holds in the particular setting that we're looking at. And we give a corresponding sample complexity upper bound. We give an algorithm. So notice that in the high temperature regime, this e to the 2 beta is just a constant. So this is indeed like matching. And we also get a linear time algorithm with this optimal sample complexity. And so we've resolved the question in the high temperature case. Okay. Now I'm going to be talking about the classical setting, sort of how the classical algorithm proceeds. Now, as I mentioned before, the classical problem is what happens when you restrict to diagonal Hamiltonians. So this is just Pauli Z gates, Pauli Z operators. And in this case, the Gibbs state is also diagonal, a diagonal density matrix. And so it's just a sample from a classical probability distribution. In particular, the distribution is called a Markov random field. And for example, we could look at the Ising model. So this is the model where we're on a 2-dimensional lattice and all the terms are 2 local. So this, I'm representing a term by an edge between the two qubits or 2 bits now that it acts on. And when you take this diagonal density matrix and sort of relabel everything, you relabel the basis states as plus and minus 1. And then you get this distribution, which has the density described here. The density described here, which is the standard form in which you see the Ising model being defined as. And the interesting thing about these Markov random fields, these classical Hamiltonians, is that they satisfy what's called the Markov property. And what that is that what it says is that if you have some region and you condition on the boundary of the region, so here I've conditioned these 4 bits to be plus 1 or minus 1, then once you condition the resulting distribution on the rest of the bits can be split, and the inside piece is independent of the outside piece. So to show this is like an exercise, a simple exercise, but basically what happens is that you can look at the probability distribution and basically split it into pieces, the piece that is inside the region and the piece that's outside the region. So the piece that touches xi in this case. And so you notice that if you condition all these xj's to be plus 1 or minus 1, then you immediately get that these terms only depend on xi, and these terms only depend on things that are not xi. And so you do indeed get this like independence. You get this splitting behavior. And this Markov property is useful because that means that you can, when you condition, you can just sort of throw away the rest of the system and only focus on a small region maybe even in like a constant size region. And so how you would learn the parameters of a of this classical Hamiltonian from these samples, well, what you do is you just get a bunch of copies of the samples the samples from the Markov random field. And if you're trying to learn a particular parameter, what you do is you condition. So let's say I want to learn this particular the weight. Then what I would need to do is condition on the things that are adjacent to it. So let's say, I condition on these orange bits, and I condition on them both being plus. And when I do that, I have a conditional distribution. And I know that in the conditional distribution, this pink piece is independent of anything else outside. So it's independent of anything outside. And so what I can do is I can just learn the distribution on these 2 bits, which doesn't require too much because it's only, you're only learning 2 bits. And then you can use that to determine what the corresponding term is, this lambda ij is. Now, this gives you the optimal time complexity and optimal sample complexity. It shouldn't be obvious that this is true, that this algorithm that I've stated works. I've just given an outline. But basically the only thing that you need to see is that, first of all, the Markov property allows you to get a handle on this lambda ij without any sort of interference from the outside of the subsystem. And you also need to show that when you perform this conditioning and when you use the conditional distribution to learn the lambda ij, you don't need too many samples to perform each of these steps. So that's all you need. And once you have it for one particular term, you can use the same copies for all of the terms. And so you can get all of them with only paying an additional log factor in the number of terms. Okay. Now that was a bunch of details, but the main thing is to keep in mind is this Markov property. And the reason why you could keep it in mind is that this is like the fundamental issue with trying to generalize this problem to generalize this algorithm, because it doesn't really hold, this like approximate Markov property doesn't exactly hold in the quantum setting. The Markov property doesn't hold in the quantum setting. There are approximate versions that do hold for sufficiently small beta. I've written some like examples of like potential generalizations, but essentially what this amounts to is saying that if you are looking at a particular region of interest, A, then you can throw away everything that's distance delta away from A, so this region C, and still not lose the information that was contained in A. So you're still able to learn A even if you just ignore C. And here this delta is like log 1 over epsilon. And the thing to observe is that while this does restrict you to a smaller subsystem, it's not small enough. Because this ball, this A union B, could potentially be like log to the D 1 over epsilon many qubits. And so if you wanted to perform like like tomography on this, it would be quasi-polynomial time in epsilon. And so it's not really small enough. So what we're going to do is we're going to look at, in order to get around this, we basically just look at a more refined analysis for how these bounds are proven. And this will turn out to be enough to give us the algorithm that we want. But it's a sort of roundabout way to get there. So let's begin with how AAKS gets their sample complexity bound. So how the prior work is able to get their sample complexity result. And the key idea is that there's this observation that if you know these expectations of observables, trace of EA rho, if you know them for all of the terms EA, then it actually determines the parameters of rho. So you can think about this as similar to the result that a Gibbs state is the maximum entropy state satisfying linear constraints that look exactly like this. So it's sort of like a similar thing. And what one should notice about this claim is that it's essentially saying that there are these terms, these expectations of observables, these values, which are easy to estimate given copies of rho. So these, it's a simple procedure to estimate these if you have copies of rho. And using it, you can actually sort of information theoretically determine the parameters from this. Now, in order to make this rigorous, you have to perform the error analysis. So you have to do this with error. And the way that one would do this is to get a bunch of copies of rho of your Gibbs state, and then get estimates to all of the expectations up to some epsilon factor. And then after that, we want to try to find and output any parameters. So as our guess, we want to output an estimate of the parameters. And so the way that we choose our guess is we just want to choose something that matches the expectations that we estimate, the expectations that we see. And because the expectations are similar, we say, okay, maybe the parameters are similar. And indeed, we know that this is possible to output some setting of parameters, because if you take, there is lambda tilde equals lambda as an option. So it is possible to, it is always possible to, there is always one parameter setting that satisfies this condition if the quantum part was done correctly. And as I just mentioned, this algorithm works information theoretically if you can say that the expectations being close means that the parameters are close, up to perhaps some constant L or some factor L. And you can sort of see why this is true just from, you can see why this would suffice just because it follows from these two facts, triangle inequality. Okay. So this is the fundamental algorithm for the sample complexity bound. And I'm going to rescale everything down by L so that the output is the desired error bound. And as I alluded to before, doing this quantum part is actually straightforward. And you can get these estimates using a sample complexity of only L squared log m over epsilon squared. Now, the obvious thing you might get would have a factor of m instead of log m, but it's possible to see that you can perform many measurements on the same copy of the rho, and so that gives you log m. And if you recall from before, what we wanted can be achieved. So the optimal sample complexity can be achieved by if we are able to prove this statement for L being beta inverse. Okay. So how do we show this statement? Well, the thing to see is that this sort of looks like this sort of bound that if these two things are small, then the corresponding parameters are small. It's sort of like a Lipschitz bound, or a bound on a first derivative. Namely, if we look at this map from parameters to expectations, we can see that what we want is a Lipschitz bound on the inverse of this map. And so if you actually formalize it, indeed what you want is a bound on the inverse of the Jacobian. And you want the infinity to infinity norm to be bounded by L. And this will imply the statement that I wrote here. Now you might not see that, but it should, hopefully it's like clear intuitively why this is the case. Now, AAKS essentially analyze this object. So they don't say that they analyze this object. They say that they show strong concavity of the log partition function. But this is just a 2-to-2 bound of the same inverse Jacobian object that I've written here. So this is another way of viewing their result. Okay. Now, how are we going to bound this inverse Jacobian? We will use high temperature, the high temperature assumption fundamentally now. And we will use this technique called cluster expansion, which essentially says that we can expand the log partition function into a multivariate Taylor series, and the multivariate Taylor series will converge for sufficiently high temperature. And so we can write these expectations as also as power series in the parameters, because they're just derivatives of the log partition function. So in this way, we have some like power series representation for these expectations. And this is relating the parameters to the expectations in a very concrete way. And so I've just rewritten it here and written out the first couple of terms. And now what we can do is we can just analyze the Jacobian and see if it indeed has the right bound. The regime to keep in mind is that gives the intuition is the beta going to 0 regime. And in this beta going to 0 regime, all these terms sort of go to 0, and only this beta XA term matters. And if you look at this map of like if you look at this expression, this just means that the Jacobian tends to beta times the identity. And so that means in this setting, J inverse is 1 over beta times the identity. And so its infinity to infinity norm is also 1 over beta, which is exactly what we wanted for the optimal sample complexity. Now, outside of this beta going to 0 regime, we still have beta being relatively small. So you can imagine that the contribution of this beta squared and up piece is still small. And so this is indeed what we show, which is sufficiently small beta, you get essentially the same bound with just a constant factor loss. Okay. And so, right. Now what we do is we have our sample complexity bound. Now how can we make it time efficient? And the way that we do this is by going back to the algorithm that I mentioned before. And this algorithm I argued was like information theoretically, worked information theoretically. And to make it work time efficiently, I already argued previously that this quantum piece could be done efficiently. You'll just have to believe me, I guess. And the main thing to worry about is this classical piece, because you have a bunch of these estimates and you want to find some lambda tilde that gives you all the expectations that are close to that. Here, by the way, I've replaced this epsilon over L with beta epsilon. I've just replaced the L by the optimum value, which is like the beta inverse. Okay, so how do we do this classical piece? Well, we look at this expression here, and we expand it using the multivariate Taylor series expansion that I mentioned before. And then because it converges, we can truncate it. And we can truncate it without too much error if we truncate at log 1 over epsilon many terms. And then we consider this function and try to find a value that makes it small everywhere, right? Because ultimately we wanted all of these estimates to be close, and this just amounts to this cal f being small everywhere. Or in other words, x being an approximate 0 of cal f. And now this is just the task of finding a solution, an approximate solution to a system of polynomial equations So we can just use standard methods like the Newton-Raphson method for root finding, which is just some optimization method that will give you an approximate solution quickly. In particular, we show that it takes only a log number of iterations. And the main factor in the complexity here is actually just computing all of these polynomials, because they actually have an exponential number of terms in M. But an exponential number of terms in M is just going to be epsilon, 1 over epsilon to the 0.7. And it will turn out that the quantum piece will dominate because it's 1 over epsilon squared. And so because the quantum part dominates, that part is just linear time and then the sample size. And so this is this gives you an optimal time complexity algorithm. Okay, so that's the algorithm. Thank you for listening.